Hello, good afternoon to everybody, and my name is Arvind, and I work as an application engineer in EMWorks. And on behalf of EMWorks, I welcome you all today for attending this webcast. Okay, there are a few attendees who are just joining in, so for their benefit, we'll just wait another 1 minute, and then we will start this webcast.
Can you hear me?
Hello?
Hello?
Yes?
Can you hear me?
Yes, I can.
Okay.
Hello, Adam.
Hello, you're on the right meeting. Hello, this is Adam.
Okay, we will start to commence our webcast right now. Okay, again, welcome to this webcast. This is about EMS for SolidWorks. My name is Arvind, and I work for EMWorks as an engineer. Okay, the agenda for today is we will talk a little bit about the company and its products, and then we will delve right into the industries and the applications, and then I will actually show you a few real-life examples that were solved using EMS, and finally we will wrap this session with some question and answers that you may have. Okay, I want to remind you, our viewers today, that we have a chat window right in your GoToMeeting. So as and when you feel like typing in a question, please feel free to do so during the presentation, and at the end of the presentation, I will be happy to answer all of them. Okay? So let's start with who is EMWorks. EMWorks is a company that was one of the first to actually embed electromagnetic simulation inside CAD. Okay, so we could call ourselves some kind of a pioneer in CAD embedded simulation for electromagnetic, electrothermal type of applications. Okay, we have two products that are completely embedded inside SolidWorks. One is EMS for SolidWorks that deals with electrothermal motion application. Okay, and which will be the topic for today. And another product is called HFWorks, which is a high frequency passive RF and microwave simulation product, which is also completed embedded inside SolidWorks. As far as our products go, they've evolved quite a bit. Way about in 2008, we became a gold partner of SolidWorks. And then we embedded our solutions, both EMS and HFWorks, inside SolidWorks. Then in 2010, we added the thermal solutions. Now thermal is an add-on to our electromagnetics, so you can solve multiphysics problems that involve electrical and thermal applications. Then in 2011-12, we added a motion simulation as a part of our offering. So now users can actually do coupled problems that involve magnetics, motion, as well as thermal. In 2012, all our solvers took advantage of multi-core processors. Now this means that most of my problems that took many hours to solve can now actually be solved in a matter of minutes with modern day machines. Okay, and finally this year we'll be happy to announce that we will couple our solutions with linear static type of solution simulation. Over the years, we have gained the trust of many SolidWorks customers. That is because of our relentless pursuit of improving the product and making it usable, making it look and feel very similar to SolidWorks, and also to make them easy to use while not compromising on features, functionality, or accuracy of the solution. So these were the reasons why many SolidWorks customers have adopted us as the mainstream solution, as their mainstream solution for their electromagnetic applications. We are way past 400 customers starting this year, and we hope by the end of this year we will reach a target of 500 customers. What are the products that we offer? The topic for today is EMS, so we will talk a little bit about the electromagnetic solution that's on your left hand side as you see your screen. We have two types of main bundles that cover the EMS product. One is called EMS Professional. EMS Professional comes with 5 different types of solvers. It comes with the electrostatic solver, the electric conduction, magnetostatic, AC, and transient magnetic. In addition to this, EMS Professional allows you several add-ons. A couple of add-ons that I had mentioned to you earlier in our progress chart is coupled to the thermal simulation, and the other one is coupled to motion simulation. Now, we also have a product called EMS Premium, which contains everything that is there in EMS Professional. On top of it, we have parametric simulation, which allows you to take in any model geometry as a parameter and solve your problems. And this can actually be used to optimizing your designs. In addition to it, you will get the facility to couple with thermal and couple with motion. And all of our products are come in a network license as well as activation-based license. Network license carry a small additional fee that allows you to float your licenses within your company, whereas activation-based licenses are a standard type of licenses that come standard with the price, and that allows users to actually activate the product and use. So activation license also means that you can deactivate and activate in more than one machine. So it does have some convenience of a network license, but does require you to have internet connection connecting back to our server when you activate and deactivate. And finally, the passive high frequency simulation for passive components helps you. It has 3 different solvers. It helps you to compute the S parameters. It also has an antenna solver and also has a resonance solver. As far as the industries and application goes, some of the main industries that we are present today are, the first one is in the actuator industry. So linear actuators, rotary actuators, motors, generators, solenoids, etc. They form a bulk majority of our customers. We also have use in the transformer and inductor industry. Then AC simulations come use in people who design bus bars and conductors. Finally, we also have applications that involve inductive heating, etc. And last but not the least, magnet arrays and permanent magnets based applications also form a large chunk of our customer, especially in the recent years, recent few months. We see a lot of surge in the use of permanent magnets to design innovative devices, both in the field of consumer electronics, consumer products, and medical. Now, how does EMS actually help someone in the actuator industry? So, as far as these classes of problems are concerned, EMS simulation can actually help you to compute engineering quantities like back EMF, induced voltage, inductance, etc. of your coil. Okay. It can also help you when you couple it with motion. It can help you to predict the motion of your solenoid. Help you to predict the motion of your motors and so on. It can also aid in sizing of coils. Obviously, one can find out the forces and torques acting on all ferromagnetic substances in your design. And finally, you can actually parameterize things like geometry parameters, dimensions, current, number of turns, etc. And they can actually be used to evaluate the performance. They can be varied to use to evaluate the performance of your design. In the transformer, inductor, and busbar industry, EMS can actually help you to visualize the complex electromagnetic field that's there inside your model. In addition to it, it will be able to compute all losses in your core, and also the ohmic losses in your coil. It can aid in helping you with designing your laminations. It can compute the effect of laminations on the losses. It also has multiphysics capability, as I mentioned earlier, to see the temperature distribution across your geometry. And also one can compute things like thermal stresses, etc. For induction applications, EMS can actually help you to choose the right coil design that can serve your need. It will also compute the temperature distribution due to inductant heating, and also compute the eddy currents generated and the corresponding losses which result in heat. As far as the permanent magnets and magnetic arrays are concerned, EMS can help you design magnetic arrays for various applications. For example, we will be later looking on an example of a magnetic clutch. It can also compute the forces and the fields inside your model. And also finally, it can study the interaction between the various magnets as they are placed in an array, and how they can cumulatively act in your design. As far as some of our application goes, towards your left you see that mainly we focus on electromagnetic and electromechanical design for our EMS products. Basically, if you have any excitation that ranges from DC, AC, pulse, at frequencies ranging from say 50-60 Hertz all the way to a few hundred megahertz, we will be able to support and do those kinds of problems. Okay. And here are the list of the applications and key industries that we feature in. Mainly, a lot of our customers belong to the transportation sector, to the defense, energy, and off late to consumer goods, and also a lot of medical, biomedical type of applications. But magnetism and electricity is a field that has wide range of applications, and that feature in many industries ranging from energy to water to defense to solar, etc. So I think there is innumerable possibilities of our solutions playing a vital role in your designs. Mainly, they can be used to design motors, generators, linear actuators, magnetic recording devices, solenoids, loudspeakers, etc. Permanent magnet-based devices can also be designed, sensors, high voltage, high power applications, transformers, inverters, bus bars, and also one can study electromagnetic shielding, electromagnetic interference, etc. using this product. Our high frequency product, on the other hand, which is not really the topic for today, but nevertheless it's a good time to mention that we can deal with something for a few hundred megahertz all the way to 100 gigahertz. Frequency excitation can actually be dealt here. So it can aid in the design of passive RF and microwave components, antennas, filters, couplers, etc. Again, traditionally the use has been more in defense, in aerospace, and so on. But right now, with antennas being embedded everywhere, including watches, cell phones, computers, etc., it's pretty much a very big industry in the consumer goods space. So there's a lot of applications in Medicare, consumer goods, etc., which make use of the high frequency product. Well, I'm going to run through a few examples. So we're going to take a look at a magnetic circuit. We're going to take a look at solenoid type simulation. We're going to take a look at magnetic array and finally a motor. So what I'm going to do now is I'm going to switch myself to my SolidWorks, where we are going to take a look at a few examples. So I'm going to start with a simple magnetic circuit here that I have. And this was designed using SolidWorks, and the objective of this particular simulation is to compute, is to first visualize the electromagnetic field present in the geometry, in the ferromagnetic substance, and as well as in the air surrounding them. Number two, we are interested in computing the inductance of my coils here, and finally, what is the torque acting on this movable part or the rotor. Okay? This is a very simple magnetic circuit. It carries current in both these coils, and once the coils are excited, it creates a magnetic field, and it actually creates a magnetic circuit. Okay? This was done using SolidWorks and was analyzed using EMS. As you see here, EMS simulation is actually organized as a design study right inside your SolidWorks. Okay? It carries what is called as a study, which helps you to do all your designs. It also has a list of the parts here, and it has its own material. So the parts actually, the materials can be applied using an EMS material library that comes standard with the product. So it has a lot of steels material which is pre-populated with the BH curve, etc. It also has conductor materials like copper, gold, aluminum, etc. It also has a list of neodymium and ceramic or samarium cobalt based permanent magnets. But the good thing about this material library is it is completely customizable, and hence users can actually create their own material and use that for simulation. So in this particular model, we have the outer core that is made of steel. It's actually steel 1010. The inner rotating core is also made of steel 1010. And then the coils obviously are made of copper. And notice that I don't have to model each strand of copper as a coil. So the volume represented by the copper coil can actually be modeled as a 3D geometry, and it can be used for simulation. As far as defining my coils are concerned, now I have two wound coils. And you can see the definition of the current through my coil. So there is a current entering this particular phase, and it has 80 turns, and it carries a current of 1 amp per turn. So the coil definition is extremely simple. You need to identify the parts that comprise the coil. You need to tell the program how the current enters the coil, and also specify the number of turns and the current per turn. Similarly, we defined another coil, the second coil here. So this now talks about the current. So it's very similar to that. It's 80 turns and 1 amp per turn. So once the coils are defined, we finally request the program to compute the force or the torque acting on the rotor, on the part that is inside the steel part, which is called the inner rotating core. Okay. Now the result table organizes. I've already run these simulations prior to this particular demonstration, so I'm going to go over the results directly. The result table pretty much gives you all the engineering quantities that is of interest to you. For example, the torque about the z-axis is computed here. That's about minus 1.3 millinewton meter for the excitation that we applied. The program also computes the inductance matrix of the coils. We compute the self-inductance as well as the mutual inductance, and it also computes the flux linkage associated with the coils. Okay, once you have these engineering quantities, EMS is a completely 3D field simulation software. So we will be able to display the results in a 3D, visually in a 3D space. So here you can see a section plot of my magnetic flux density inside my model. You can see areas of my model where you have high values of magnetic flux density and areas which have low values of magnetic flux density. So this is a section plot. One can also plot my magnetic flux density as a vector. So here the same result can actually be visualized as a vector. You can see how the flux lines go in this circuit. And the values and their values at various points. Okay, so this is the magnetic flux density plot. You can also visualize the magnetic field intensity, that is H amps per meter, and here you can notice how it is in the air gap. So one can also take a look at the results in the air. So I'm going to go ahead and show the air and see the magnetic field intensity, and I can go ahead and take a section view. So you can view results not only in your solid model, but also in the air region around your model. So this is the magnetic field intensity in your model. So EMS, the 3D visualization of EMS enables you to actually intimately understand your designs. So you can actually compute their field intensity and visualize them at every location in your model. So there is no more guesswork. There is no more any analytical methods used to compute where it is. You can always see that the field intensity is very high in the air gap, the space where there is air gap and where the magnetic circuit is going to close. Yeah. Okay. Now, doing design changes in EMS is extremely simple. So if I have, for example, I want to change the design of my inner rotating bar, so I actually can execute the design change in SolidWorks, and I created a new study for this design, and you can actually use it to compare the magnetic flux density for a new design. So this is obviously, you can see this is a much different design than the first one you saw. So this is the magnetic flux density if I change my inner core. And just for comparison, we're going to look at the previous one. So you can see that there is a design change in the model. So this has a much smaller volume, and the second one. So doing design changes is easy, and one can actually maintain the changes in the SolidWorks design as a part of the simulation. And you could also compare the two designs using EMS. And for example, if you want to compare the torque acting on the rotor between the two designs, so you can see the torque acting on the rotor between the two designs. So one was 0.13 millinewton and the other one is 0.15 millinewton torque. So doing design changes in EMS is extremely easy because it is tied and works hand in hand with SolidWorks. Okay. So let me move on to my next example that I wanted to show you. Next, we will talk about solenoid. So, to better view this, I'm going to take a section view inside SolidWorks. So here is a solenoid. You have a coil which is excited. Then you have a plunger that is forced back and forth due to the excitation of the coil. And you have a steel material which forms the outside of the solenoid, as well as the plungers and the stationary part. is all made of some kind of steel. So the objective here is to see how, if you apply some excitation, what is the force acting on the plunger and what will be the movement of the plunger as a result of this force. Okay. So in this particular problem, we are coupling the motion. We are coupling the the electromagnetics to SolidWorks motion. Okay, that allows you to do solenoid these type of problems. Okay. Okay. So now what we did is we have a SolidWorks motion study, which simply tells SolidWorks motion that there is going to be some force acting on the plunger, and I'm making that force as 0 newtons. It tells SolidWorks that the EMS is going to give the value of force, and based on the value of the force, which is going to change at each instant as the plunger moves inwards, it will calculate the next position and so on. Okay. This is in conjunction with SolidWorks motion. Okay. Now one can actually take a look at some of the results. So here is the results of my magnetic flux density inside my solenoid, and I can actually go ahead and animate it, and you can see how my plunger actually moves inside due to the excitation of the coil. So as the plunger moves inside, you can see the flux being developed in the stationary part, and it can actually be visualized nicely for this. Now next we take a look at the result table. Now result table has a plethora of information. In this case, first of all, you can plot the center of mass and of the plunger and how it varies as a function of time. One can also take a look at say the velocity of my plunger and how the velocity varies as a function of time, and the acceleration and so on. Okay. And then you can look at the force. In this case, it's the force acting in the y direction, and you can plot the force at each instance of time. So obviously the force initially is very small, but as the plunger moves in, the value of the force actually becomes large. And the force is in the negative direction. It's just for people who are wondering, it's in the negative x direction because the positive x is against the movement of the plunger. So this is the force acting. And you can get the force acting on the plunger at every instant of time. In addition to the force, the program also calculates the back EMF on the coil. So this is the back EMF of the coil as the plunger moves in, generated in the coil. Also, it computes the inductance of the coil and the flux linkage as we discussed about earlier. So this is the variation of the flux linkage as a function of time. So all of these engineering quantities are obtained, and of course there is also an option to view results not just as a scalar, not just as a fringe plot, but also as some kind of a vector plot. Here I am viewing the same result as vector, and I can actually even animate the motion of the solenoid, and you can see the transformation or the modification of the vectors kind of denotes how the flux actually moves as the plunger moves inside. So this is this example again, just to reiterate. You define a study, you select your parts, and you define materials. Then you define request the program to compute the force, on the movable part, and then you also define a coil. In this case, just like the previous one, there is an excitation in the coil, there's a certain number of turns, and there's a current value per turn. Next, we're going to move on to an example that involves permanent magnets. We've not seen that so far. Now, this is a magnetic bearing, so it has like 6 different types of magnets arranged, 3 inner magnets and 3 outer magnets, and the direction of the north-south of the magnets are in such a way that there's always a force on the inner magnets that prevents it from going too far away. So this acts as a guide for bearings. Now this is a magnetic type bearing, so there is no need for ball bearings or any kind of lubrication. So the inner magnets and the outer magnets are always held together by a magnetic force that actually acts like a bearing. So in this example, again, so I have several materials. There is the inner magnetic array, the outer magnetic array. Now we'll just take a look at the inner ones first. So as far as the magnets are concerned, you have to define the direction of coercivity, or the direction, the north-south direction of the magnets. The north-south direction of the magnets can be defined in terms of both global and local coordinate system, and here you're defining it based on Cartesian or cylindrical coordinate system. For example, here in the first magnet, the north-south, it's pointing upwards, and in the Cartesian coordinate system in the y direction. In the second magnet here, this is where we're going to apply a coercivity radially. So now I've created a local coordinate system inside SolidWorks, and I'm used it to apply to create a cylindrical coordinate system, and use it to apply a cylindrical coordinate system where I can define the magnets radially outward. And similarly, in the and this one, the magnetic coercivity direction is in the y direction downwards in a Cartesian coordinate system. So you can actually create permanent magnets and define the north-south or the direction of coercivity according to your choice, because SolidWorks allows you to create coordinate system, and EMS allows you to use them to create both the global as well as local coordinate system, Cartesian, cylindrical, and spherical type of coordinate system. So it's actually quite robust to define permanent magnets. Similarly, all the outer magnets are also defined, and the coercivity directions are defined. One requests the program to compute the force acting on the inner magnets and the force acting on the outer magnet system. And we also do this as some kind of a parameterization, where I have got a dimension which is the distance between the two magnets, two sets of magnets, as a dimension, as a parameter, and I'm going to vary that dimension, the distance from 2 millimeters all the way to say 20 millimeters. So just to give you an idea, we have a SolidWorks mate which talks about the distance between say the inner set of magnets and the outer set of magnets. Now this distance can actually be created as a parameter, which is what is done in EMS now. Now this distance is modeled as a parameter, so which means I can vary this distance, and I can study what happens to the simulation at each distance. So again, in the result table, one can take a look at the force, for example, acting in this case force along the y-axis, which is the major force, and how does it vary according to scenarios. So you can see at a distance of 2 millimeters, the force is about 450 newtons, and the force keeps increasing as the bearings get away from each other. And right about 8 millimeters, the force is the maximum, about 1000 newtons you get. And then as it keeps, the bearing keeps moving away from each other, the force comes down. And also beyond 18 millimeters, the bearing is not allowed to move. The force actually changes direction, and it actually becomes a minus 150 Newton, pushing the bearing back inside. So actually, it's a very interesting phenomena of magnetic bearing, where you can actually get rid of ball bearings, get rid of any kind of lubrication, and also get rid of your stops for your bearing. So there is some range of movement which are possible, and the bearing will never get out of that range. So as before, one can actually view the flux density. For example, here I can take a section view of my magnetic flux density and see how it is distributed here, the values and so on. I can also create plots along a particular line. Here I have a 2D plot that is created between 2 points in the model, and I can study the magnetic flux density and the variation of it between any 2 points in my geometry. Okay. I'm going to use this particular example to highlight another important feature inside EMS, which is the report feature. Okay. EMS has the option to compute, to actually create automatic report based on your simulation. The report can either have a HTML format or a Microsoft Word format. Here I'm going to create a report in the Microsoft Word format. So what the program does is it automatically takes a snapshot of all the plots that you did, all the simulation parameters that you created, and then it actually opens a Microsoft Word document right inside SolidWorks, highlighting everything that was done in your simulation. So here you have a Microsoft Word document which acts as a report, and this was created inside SolidWorks. And because this is Microsoft Word, it's fully editable. I can add my comments here. And I can store this report right along with my SolidWorks file. So it contains the name of the components. It has the all the parameterization that we use. It has the result table, the forces acting, and how it varies as the scenarios. It also has all my result plots that I created, 2D as well as 3D, and it's a nice document that is automatically generated, that allows you to share your designs, etc., across your team, or also with your customers and so on. Okay. So this is a magnetic bearing example. I'm going to close this example, and last, and as a last example, I'm going to show you a motor application that was done using EMS. Again, this is coupled with motion. So here I have a three-phase motor or a generator. I can solve this problem either as a motor or as a generator. In the case of a motor, I'm going to apply current and excitation on my coils, and then I'm going to see how my rotor actually rotates. And in the case of my generator, I'm going to rotate the rotor at a certain RPM, and I'm going to see how much current is collected by the coils. So it doesn't matter the problem, whether it is a motor or a generator, EMS can deal with it. So the idea again here is to define my coils. Here I have defined 3 sets of one coil. It's an AC motor. So you have the first set of coil. I can actually show, you can see how the current branches through this coil, goes in, comes out. It forms like some kind of a loop here. It's for a three-phase motor. This is the first set of coils, and similarly the second set of coils are here, and the third. And if you look at the coil definition, now here is an AC current applied, so it has a sinusoidal type of signal, and you can see the maximum current is 10 amps, and the frequency is 60 hertz. It's a AC signal. And if you see the second coil, second set of coils, you're going to have a small phase shift in the signal. So here is a new signal that is slightly, it's 90 degrees out of phase. Okay. So it's 90 degrees out of phase. And finally, there is one coil 3. Where the signal is again out of phase now in minus 90. Okay, so so you can have a three-phase motor. You have 3 different kinds of signal with the phase difference. And again, we are requesting the program to compute the force acting on the rotor, which comprises a steel rotor and some permanent magnets that are stuck to the outside of the rotor. Okay. And all those permanent magnets definition was done in the materials. Okay, again, as in the results, as you said, one can compute, one can take a look at the torque and the variation of the torque as a function of time. You can take a look at the inductance matrix of your coil, the inductance of your coil, and how it varies, the mutual inductance as well as the self-inductance. And there's very, very, very small variation as the motor rotates, but that is also captured. And finally, the losses, the ohmic loss in the coils are also captured, and the losses in the stator are also captured here. In case of motor, these are the losses in the stator. So the losses can also be captured using EMS. Okay, and finally, looking at results, post-processing, the features that I showed you earlier apply here as well. So I can actually take a look at my magnetic flux density inside my design, is technically inside my motor, and I can also choose to animate this and see how the motor rotates, how my flux varies. Creating the frames for animation, and now you will be able to see the animation. Okay, so and you can also take a look at it as vectors, the flux density, and this is the vector plot of my flux density, how the distribution is in my motor, and obviously this can also be animated. And finally, I can take a look at the eddy currents created in the stator and how they vary. So this is the vector plot of my eddy currents generated in the stator, and this is responsible of heating the stator, and you can even find out what's the wattage, what is the loss in my stator is actually computed by the program. Okay. With this, pretty much we come to the end of the things that I wanted to show you. I want to just get back to my presentation and take this opportunity to thank you all for taking the time to attend this webcast that we had today. If you have any questions, I know we went over a lot of functions and features of the program very quickly today. The objective was not to tell you an in-depth working of the program, but also just to expose you to the various applications and the various things that can be done using the program. So please feel free to visit our website. It has a lot of information. Also, it has a link to a YouTube channel where we have many videos that shows the applications, the various applications and the functioning of our product. Obviously, you can also go online and register to download a free 15-day evaluation version of EMS and try out EMS in your own end and see how it can be of use to you. And finally, we want to tell you that we are running this series of webcasts this month, and 2 lucky winners will be chosen sometime around Christmas, and they will receive 1 year free license of EMS Professional with full support, and you will all be, everybody who attended today will be eligible for this prize. And so finally, I would just like to thank you all again, and I hope you have a good rest of your day. And right now, I'm going to just take a look at some of the questions that were asked, and I'm going to try and answer them. Okay, one of the questions that was asked is, would the same features you have presented to us work in interaction with Autodesk Inventor? The answer is yes. We have a product called EMS for Inventor, and most of the features that I mentioned here are applicable for EMS for Inventor too. There may be a few slight difference that is not easy to enumerate during this presentation, but for the most part, our EMS for Inventor product will have a very similar experience working as what you saw here. But again, it depends on your application and so on. So we strongly urge you to just take a look at our data sheet. Our website talks about the EMS for Inventor product, and you may also contact us and with your particular product, particular application, and we'll be happy to help you with it.
Arvind, this is Adam. There was a question that was sent to me, and the question is the air gap compulsory to be modeled between the permanent magnets? And the gentleman is saying, I want the force at 0 air gap. What is the best way to do that?
Okay, no problem. Is it completely necessary to model the air gap? The answer is no. If you have air gap in real life, yes, you must model it. But if you have a magnet that is almost touching or which is touching something else, there is no need for you to model the air gap. So you can actually take a look at the force acting even while the two things are touching. But ultimately, in real life, there is a small amount of air gap just to make sure that things can move around each other if you're talking about motors and so on. So it is a good idea to model the geometry as precisely as how your real life model will look like. So in that case, an air gap in 95% of the cases becomes an unavoidable thing. And no matter how small your air gap is, EMS allows you to model it, and then we will be able to compute the force across the air gap. Okay, there was a question about the interference. how does EMS behave in case of overlap inside parts of a 3D model? Actually, to answer that question, we should not have interference for your EMS study to run. So one of the first things before you launch the solver, we do is we check your model for interference, and if there is an interference, we do warn you and we stop the simulation. So for your assemblies, you should not have any interference between your parts for EMS to work properly.
Was another question. There's another question, Arvin. The gentleman is saying, how does EMS behave in case of overlaps inside parts of a 3D model?
Yeah, there cannot be any overlap inside the part for a 3D model. So EMS will not function if you have overlaps or interference between parts. So you'll have to resolve them and make sure that there is no interference in your geometry before you run the simulation. Is there a possibility to link EMS with the flow simulation? At the moment, it's not possible. However, we have a very limited thermal EMS and thermal application. It's not really a fluid flow application, but with the thermal, it will help you to compute at least the conduction part of it, the heat transfer through your solids, which is now created due to the load generated by the electromagnetics. It's possible. So right now we don't have any tie-up with SolidWorks fluid flow. Hopefully in the future that's something that is going to be looked upon.
There's another question, which is, does EMS use its own resources for combined thermal motion electrical simulation, or it needs Autodesk Inventor resources?
I think, I mean, to answer this question, it's actually, EMS is a CAD embedded solution, okay, EMS for Inventor or EMS for SolidWorks. So obviously there's a lot of dependence and a lot of interaction that happens between the CAD and the simulation. So you cannot say that EMS is completely independent. But on the other hand, it's meshing, it's solving, it's post-processing, even though it's inside the CAD window, does not really interact much with the CAD. So it's only for the geometry information that EMS interacts with the CAD. By the way, thermal, even for thermal, it's not the case. We do not have motion simulation with Autodesk Inventor. It's only present using SolidWorks.
And another question, which is there a possibility to link EMS towards the flow simulation tool for SolidWorks example for transferring data, example losses?
No, it's not possible at the moment. We do not couple our solution with SolidWorks flow simulation. It's something that we are going to look into in the near future. Yes. However, there is one thing that you can do. EMS gives you the wattage, the loss that in terms of watts for your different components. You can actually take that value and then apply it to the entire body inside your SolidWorks flow simulation. It's not the, probably it's not the very, I would say the most accurate way of doing it, but nevertheless can give you an idea of what type of cooling can happen inside your model.
Another question is the integration with the Inventor seamless?
Yes, the integration with Inventor is seamless. It will be very similar to what you just watched here. My sincere request would be to just go to our website, or you may contact us at support or at sales@emworks.com, and we will be happy to schedule a one-on-one demonstration with you, where we will be able to show you the product, in this case Inventor, for EMS for Inventor. And there is one more question. In the case of permanent magnet machine tables, I think that this is a very specific question which relates to this one. So maybe it's just good to take this offline. We would be happy if you can contact our support person for this specific question that you have, and we'll be happy to just help you with that. Is there access to getting started as PDF file? Yes, absolutely. There is a getting started that we've just prepared as HTML with videos and so on. It'll be shortly available on our website. You know, we're just talking about a few days, so as soon as it's there, we will intimate you. But what do we have right now as resources are the following. We have EMS tutorials, which contains many problems, and you have access to this. So we have tutorials. On top of that, we also have what is called as a EMS demo viewer. An EMS demo viewer comes with a set of problems that you can actually view. The problems are already set up. A small description of the problem is given here. As you see, we have several different industries and applications. You have different problems. So all of them are kind of listed here. So you can take a look at some of these problems, and you can actually do them, and we keep expanding these problems. So these are some of the resources that you have to learn the software, which is probably sufficient. In addition to that, we do provide you, if you need some kind of online training on an hourly basis, just to help you get started with the. But the getting started type of is going to be launched very quickly. You'll have access to it through our website. Also, there is going to be a PDF and a HTML based getting started in EMS. Okay, with this we pretty much end this webcast. I sincerely thank each one of you for having taken the time to attend this webcast, and look forward to having interactions with you in the future, and wish you all a very pleasant day and happy holidays in December. And thank you very much. We will.
I would like to remind everybody that the two selected winners of the 1-year license will be notified via email before the end of this month. Thank you all again. Happy holidays to all, and have a good afternoon. Bye-bye.
Thank you also.
You're welcome. Bye-bye.
Yeah, thank you very much.
You're welcome, sir. Bye-bye.